So previously on my channel, I made some videos about writing emulators for Sinclair computers using only ANSI C. And in this video, I've added a little BP speaker to my Sinclair Spectrum emulator so that it produces sound like the Sinclair Spectrum did. And I'm driving off of a GPIO pin coming from my Raspberry Pi. I've got 5 volts GPIO pin, which is GPIO 11, and ground. And I'm just using a transistor to drive the little speaker. And in this video, I will go over a demonstration of actually in use, and then I'll go through the electronics and the circuit and describe how the circuit works and go through the source code ultimately. So I've got a game running on the emulator here, which is Sablewolf. And if I just start the game, so you can hear the speaker in use already, and I'll just kill myself so that I can get to the theme music. So now the theme music's playing, and I've got a little potentiometer on here so I can adjust the volume of it, and I can turn the volume of the sound right down or up. And that's different to the Sinclair Spectrum where you couldn't adjust the volume, but this goes to a louder volume than the actual Spectrum itself, so it's handy to have that in there. So this is the circuit, and it's very simple. So the audio input signal from the GPIO pin comes in here. It goes through a 1K resistor, and that 1K resistor is there because I've got a potentiometer here, and I want at least 1K going into the base of that, because otherwise it'll overload the transistor and below the transistor. And the transistor can be varied. The input of the transistor can be varied anywhere between ground, so that when it's silent, using this potentiometer, or up to the GPIO pin level, voltage level, which gives full volume control. And all the transistor does is it makes the circuit between the loudspeaker and ground. So in the top here is 5 volts coming in the top, and the transistor just allows that 5 volts to flow to ground when it's switched on. And you really need a diode here, because the loudspeaker, even though it's very tiny, it has a little coil in it, so it's got an inductor in there. So when you turn the power on through this speaker and then switch off again, you get a reverse EMF. So you get a reverse voltage, which tends to hold the speaker switched on. So in order to prevent that, have a diode there. And if you try the circuit out and you remove the diode and put it back in again, you see it makes a big difference to the volume that you get out of the loudspeaker. Because I'm only driving this from a digital signal, so it's not an alternating current. If it was an alternating current, then the speaker would be driven low and high in both directions, but I'm only ever driving it low here, so you need that diode in there, very essential. So in the emulator code, I've got a callback for I/O ports, and this is one's for the keyboard where the beeper is actually connected to the same port. And in that, if the port direction is an output, so an output would be to the beeper, and the actual data bus indicates that the beeper is being outputted to, then I call this function to log that there has been output to the beeper, and I pass in the current clock cycle count from the CPU, and otherwise I indicate the actual beeper is turned off and give clock cycle count for that as well. So this is the driver for my beeper, which is separate code to the actual emulator itself. So if I change this, so if I want to run it on, say, a microcontroller, I should just have to change these drivers, and without having to change any of the emulator stuff, and the emulator stuff should just compile and work as is. And in here, so I'm using the Raspberry Pi. I want to identify the model of the Raspberry Pi, because GPIO is memory mapped, and in each model of the Raspberry Pi it's in a different part of the memory. So I read this file on the system, and if you look at this file yourself in the command window, it tells you what the actual model of the Raspberry Pi you're running is. I've got this function as well to map the GPIO memory. So you have to actually allocate memory that you're going to map over the GPIO area so that you can then use it, and you have to align it to a 4K page, which is done here. You can actually use a library and make it much simpler for you, but I quite like using the direct routes because it keeps the code light, and there's not that much to do. It just looks a little bit more complicated than it is. And then this function maps the memory into the allocated memory that we allocated up here, and we're going to use to actually access the GPIO ports. And then I just return a pointer to the memory that I've just mapped so that I can use it in my code. So at the start of my emulator, I will call this init function, which sets up the port how I need it. So I have to open the memory device on Linux so that I can actually use that to access the GPIO ports. Here I'm calling the function which I went through above, which actually gets me the Raspberry Pi model name back. And I'm doing comparisons here to see if it's a Raspberry Pi 4. And if it is, then I use this offset. Or if it's a Raspberry Pi model or Raspberry Pi 0, then it uses this offset, which is the original. Otherwise, I assume it's a Raspberry Pi 2 or 3, and it uses this offset here. So I call the GPIO memory, which is the function I described above, and I use the base address of the I/O, which is what I found up here, and add the GPIO base to that. The GPIO offset, the offsets are all the same in all of the models. So once you've got the base address, you can just use the offset you need, and I get then the pointer to the actual GPIO memory. So now it's a lot simpler to understand from here on, because all I need to do is I can set it as an output. So I set the GPIO pin 11 as an output. So I'm going to use that for the beeper, and as that's the only pin I'm using, that's as complicated as it gets for setting, configuring the actual GPIO as I need it. Now I'm going to create a thread of execution, so I'm going to run this audio driver a separate thread of execution to the emulator itself, so that this doesn't get in the way of the emulator and the emulator doesn't get in the way of this. They both sort of need to run and keep execution nice and to themselves, so they both have their own thread of execution, so that they can actually just dominate that thread of execution. So then I just so you have, when you create a thread of execution, you pass in the set of variables that you want to use. So that if I pass in the pointer to a structure, I can then change the values within that structure outside of the thread, and then the actual thread itself can read those values. So I can pass in and out values using a structure, but I'm just resetting that structure to 0 value. So all of the variables within that structure will be 0 value. I then create the thread of execution, and this is what I call the function, which will be defined below. So that's the function I'm creating as the thread of execution. And when I come to terminate the thread, all I have to do is pass in, this is the variables which I passed in as an argument. And like I say, I can influence the thread by setting this to the exit flag to true in that structure. And then within that thread, I can read the exit flag value. And I know that outside of that thread, I want the thread to exit, and so the thread will do that. And I just give it a second to the thread to do that, and then I turn off the beeper. I make sure it should be off anyway, but I make sure it's switched off, because if you leave the beeper on, it can get quite warm. So you want the idle state of the beeper to always be off. And here below, this is the function which I called from the actual emulator itself, which I went through at the very beginning of this source code explanation, where it passes in whether or not the beeper's on or off, and the actual CPU clock value, because here I calculate the difference in count of the CPU clock, so I know how many clock cycles occurred since this function was last called. So then I can work out the mark space ratio, how long the audio was on for and how long the audio was off for. And I just make sure it's not a length of time too long, anything invalid. I just want to keep it a reasonable length of mark space ratio, something that makes sense, something which is within the audio frequency. And I decide whether or not the actual speakers on or off, because I'm going to record mark and space ratios separately so that I can play them back. And here what I do is I write it into a circular buffer. And so you don't need libraries for a circular buffer. You can just simply do it with very few statements themselves. And so this is the mark ratio. Taking the clock count, the difference in the clock count, I multiply it by 300 so that it scales it up to the audio frequency, because this is just the Z80 CPU clock which I'm emulating, and I need to turn that into a real world nanosecond value which I'm going to delay for. So that's what I'm doing here, where I'm multiplying it by 300, and I set the off period by default to 0. So because this is the first value which is going into this circular buffer as a pair of values, mark and space. When I write the on period, I'm also going to write an off period and assume it's 0, so that there's nothing in this circular buffer from last time it came around that's going to cause a problem. And if the phase is actually in the off, if it's in the space period, then I just write the value into the space, and I scale it the same, 300 times the clock difference. So now I have a pair of values. So each time I call this function, I write a mark and a space value into the circular buffer. Then I can play it back at will. So this is separating the emulation execution from the playback of the audio execution. So they're two separate tasks. So this is the actual thread itself. This is what's actually going to play back from my circular buffer. So I've been writing values into the circular buffer. I'm going to play them back now. And so it assumes that the exit flag is false before it goes into this loop. And it just keeps in that loop until I tell it to exit that loop by setting the exit flag, as we saw above. And if the read pos of the circular buffer is the same as the write pos of the circular buffer, that means that there's nothing in the circular buffer. So I'm going to have what I call a yield period. This is how long this thread's going to sleep for. And by default, it's going to sleep for 5 milliseconds. I think I've tuned the values since then, so I think it's more like 25 milliseconds now. But this is the default when the actual audio is not playing. So how long the thread's going to yield for, so that the thread doesn't take up all of the processor time in whichever core it's running in, because it's probably going to be running in a separate core to the emulator core. And here, because like I say, the circular buffer is empty, so we're not doing anything. So make sure the speaker's turned off, because you don't want in the idle state, the speaker's always got to be switched off. So wherever we can reasonably do that, we always make sure that the speaker's turned off just to be safe. It should naturally turn itself off at the end, but you never know. It can always get into inconsistent states. So just safe programming. And this is where there is something in the circular buffer. So I decide what the phase is that I'm currently going to be of the audio which I'm on, whether it's a mark or a space. So if it's a mark value, so when the speaker's on, I know that I need to look at the next. I need to go to the next value in the circular buffer, and I get out of the circular buffer the yield period for the mark, and at the same time I read. So that's the on buffer, you see, and now on the on buffer I then set it to 0. So I've read the value out and I'm going to set it to 0, so that if I come around the circular buffer again, I don't accidentally pick up a value which was left from last time. I'm going to make sure I clear it out now, again, just to make sure that there's no accidental things occurring within this code. I change the phase to the space phase, so the next time I come around this loop, I know that I'm reading the space value. I turn the speaker on, so this is the mark period for which I'm going to yield for that period with the speaker on. But if it wasn't the mark period and it's the space period, then I read back how long that is for the period off amount of time. And again, I then overwrite that value with 0 once I've read it, just so that no data is being left in the circular buffer, which is going to get picked up by accident. I change the phase next time round to be the mark phase, and I switch the speaker off. So this is going to alternate. This is going to be like a PWM output where it changes the mark and space depending on what the program has actually done on the I/O port. It's just going to go through the buffer and do that, the circular buffer. And so this is where I yield. So at the end, I'm always going to yield. Now that yield value, if there was nothing in the buffer, then it's going to yield for something like 5 milliseconds. I think more like 25 milliseconds now I've got the program doing. If it's the mark, then the speaker's been turned on and it's going to yield for the mark period of time. And if it's a space, then the speaker's been turned off and it's going to yield for the space period of time. So this is just one yield which is going to handle all three conditions, because so it's keeping the code simple. And then after it's yielded, it'll come back around to the top again, and it will decide whether or not it's the circular buffer is empty. If it is, then it can just go into its idle state. But if it's not, then it will do whether it's a mark or phase period, and it go through the whole circular buffer, and then it will wait when the buffer's empty for the emulator to write more data into it. And once it's got more data, it'll go around and process that data and play the audio.